for lecture, we're going to be talking about electrical potential energy with the concepts of energy back in 110. And what you learned back in 110 is that energy is a different tool that we can use to analyze our systems. And in some cases, that makes our life easier. Some cases, it doesn't actually. And so there's a lot of things we are going to learn about electric phenomenon by investigating how the energy works. Because electrical energy has a lot of parallels to gravitational energy. And so a lot of the techniques we learned previously, we can apply to here and solve a lot of problems that are difficult to do. Let me give you one example of that. If you take two particles, right? Let's say you have two protons, right? Stick them right next to each other. You let one of them go, and it starts to fly away. If I asked you, tell me, after it travels, I don't know, 1 centimeter, how fast is it moving? It sounds like a simple thing to do, but it's not a simple thing to do. The reason why is because the acceleration is not a constant. And so all your kinematic tools that you had used before, they don't work now. Now you can still do kinematics, but you don't know that level of mathematics to do the more advanced kinematics. It just involves a lot of differential equations. So instead we use energy to do that. And even though the force is varying, we keep track of that in the potential energy. So anyway, all right, so kinetic energy, kinetic energy, 1/2 mv squared. That's characterizing the energy of anything that moves. Potential energy is can be determined by the work that is done by forces. The electric force is a conservative force. So the sum of kinetic and potential energies is conserved, does not change in time. So as I was just saying earlier, you can take like snapshots in time, and if you compute the total of kinetic and potential energies, that number is never going to change. So it can be compared to another time where you take a snapshot and you have an unknown quantity, for example. All right, so just a little review about work, right? Work is determined by, well, its definition is rooted in forces, right? The definition is a path integral of a force along a particular displacement, right? And so if you have a force that acts on a particle, we are only interested in its component along the displacement, which is where this cosine factor comes in. And we express this normally as a dot product. And work is positive if the force has a component along the direction of displacement. It's 0 if it's perpendicular, like in the case of circular motion. And it's negative if it's opposite the displacement, or has a component that is opposite the displacement. All right. Question for you here. Two rocks have equal, which has more gravitational potential energy? A lot of B's. A lot of B's. The answer is B. Okay, so what we have here is the potential energy is described by mgy. The further we are up from our 0 point reaction, that doesn't really matter, 0 point or not. But B is going to have greater potential energy because it's further up. So again, one of the reason why I'm asking this question, like, okay, what's the question here for, is because sometimes I think it's helpful. Sometimes I think it's helpful when you relate a lot of the ideas we're talking about to gravitational potential energy. There's a lot of analogs, and so I don't know. For me, I found it to be very helpful to do that. Oh, whoops. All right, so let's figure out what the potential energy is. We have a capacitor plate here. Plates, right? Capacitor. And we're doing this to make things a little easy right now, because the field for the capacitor is uniform, and that makes things a little bit easier for us. But what happens is if a positive charge is released, it's going to start to head to the left-hand side. So we create a coordinate system here where our negative plate is at 0, and we compare the position of this particle here at different times, and we see what the force is going to be on that particle. The force in this particle is QE, right? That's what electric force, that's how we can get electric force. And the electric field is already established by the capacitor plate, so that's our force. And that E is a constant, right? And the work that's done is, it's F times the displacement vector, and the electric field and the force and the displacement are all in the same direction here, so that statement for work is really just a statement right here. It's well, there's a negative here, that's why things are flipped around, but what this is the change in your potential energy is given by the work that's done. That's basic energy. That has nothing to do with electricity and magnetism. That's just your basic energy term there. But we could equate here that this expression for work matches a differential, right? It matches a delta U. And so we identify QES as being a potential energy term. And the U naught that's here, that's just our 0-point energy. So when you see this here, this difference that exists, that's what really matters. 0 point can be anything you like. What we're doing here is we're placing a 0 point at the negative plate here, so that when it reaches, we say that it has no potential energy, because it's not going to move anymore, because it's going to collide with the plate. So we have a U naught here out of obligation, but we will always choose a 0 point that's convenient. Just like for gravity, the ground is always, not always, but the ground is very commonly a 0 point. It's just easy to do that. So the negative plate is the ground, right? And the E is like the gravitational field here, and we have our particle falling. The further you are away from the negative plate, the more potential energy that you have. Okay, so QES, right? The S, the larger that is, the larger you are from this 0 point here, the more potential energy you have. Simple enough. Let's do a problem right off the bat. Let's just get right into it. All right, so we have a capacitor plate. We don't know the electric field. That's okay. We are told the details about the capacitor. We know that it's a square capacitor, has an area of 2 by 2 centimeters. We know the plates are charged to 5 nanocoulombs, so we want to figure out what our electric field is first. So the electric field of a capacitor is 8 over epsilon naught, which is Q over A epsilon naught. And the area is just a square, right? So it's A squared. So that's my electric field. I can plug it. I have all those numbers here. And I plugged them in right over here. So that's the Q on top. And gotta use meters. What do we say about that? So that's your electric field there. And then you just got to work out QES here. How much electric potential energy is lost as it travels from the positive to negative plate. You got to be told that distance. It's 10 millimeters. We're going to choose the negative plate as our 0 point, so that term's gone. And so the charge is a proton. So 1.6 times 10 to the minus 19. We have our electric field expression here. We got our little tiny distance. So we end up with this adorable 2.3 times 10 to the minus 15 joules. So tiny, but it's just one proton. We don't really expect it to be, what is that thing? 2.3 times 10 to the minus 15. Tiny little bit of energy. All right, again, because it's a proton. So here we go. Different configuration here. Two positive charges are equal, all right, which has more electric potential energy. Just like the gravitational question. A, huh? Not A. If you said A, no, no, no. Let's see some other letters in here. I'm just kidding. It's A. It's A. All right. So the question is this. like I said, I think it's helpful to think about this in terms of gravity, right? The ground is a negative plate. Where is A going to go, right? It's going to go up. B's going to go up. A has more distance to fall, so to speak. So it has more potential energy, all right? Excellent. So here's how it works for positive and negative charges. We have this expression, QES, right? And the potential energy decreases as we go from the positive to negative plate. Simple enough. What about negative charges, though? Because a negative charge, you're going to put in a Q for that, and you will want to put in the negative here, right? Because we don't want to put in negatives when we deal with vectors. Because negative signs in vectors start flipping things around. Directions change. So you got to be really mindful when we deal with vectors to incorporate negative signs or not. That's not true for energy. Energy is scalar. So there's no worry about, putting positive or negative things in there. You actually have to have the appropriate positive or negative things because scalars don't care about direction, right? Okay. So what does it look like for a negative charge, though? It's not different. It's not different. Okay. Now, what happens here, though, is when you have a negative charge, okay, this term is negative. We're still going to have our 0 point be the positive plate. Sorry, we're still going to have our 0 point be the negative plate. We're not going to switch this. We're not going to say, oh, now the positive plate is 0. No. The negative plate is 0. The potential energy of the electron is negative, and it decreases. So as you move to the right here, it becomes more negative. Okay? More negative. But more negative is, think about a number line, right? That is a decrease. So it's just like having a gravitational field and say you make the ground 0, but then there's a hole or a cliff or something and something falls down, right? It has a negative potential energy and it continues to decrease, but the number itself, the absolute value of the number increases, right? So this is it's a little tricky, but it's not because the formulas don't change. The 0 points don't change. It's just you got to really sort of think about what it means to have a negative energy. And electrons always have negative energy. So that's not a problem, though. Not a problem. But it's very easy to forget that and then say, oh, I'm going to make the positive plate 0 now. And then if you do that, you're going to get some wonky numbers. Okay. All right, question again. Two negative charges are equal. Which has more electric potential energy? Very good. So again, really the best way to think about this is which charge is going to fall farther, right? That's it. Because we're converting potential energy into kinetic energy. So what object, A or B is going to be moving faster at the end of this? B will. So it has to have more potential energy. Excellent. Got so many questions here. Positive charge moves as shown. Its kinetic energy does what? What happens to the kinetic energy? The answer is... We'll see what you guys say here. Let's see what you guys say. A's and C's and A's and C's. Oh, you changed it. All right, that's fine. A's and C's and A's and C's. What about B? Poor B. I don't feel bad for those options. It's got nothing going for it. It is the longer of the three, and sometimes students just guess the longer one because they feel like it's more right. But not this class. Got some smarty pantses in this class. It is C. Now, in order to do what it's doing, it had to be shot, right, toward that, because it's not naturally going to move towards positive. The potential energy increases as you get closer to the positive plate, and so we're going to see an increase in potential energy. We're going to see a decrease in the kinetic energy, and it possibly could hit the plate, right? We kind of did a problem like that, a ways back. First lecture, I believe, actually, I was talking a bit about this concept here. And we just did a basic energy problem, but it's possible you hit this plate if you have a sufficient amount of kinetic energy to do that. So anyway. There we go. There we go, right? Proton is released from rest the positive plate. It crosses the capacitor. It reaches the negative plate with a speed of 50,000 meters per second. So many meters. What will the final speed of an electron be if released from rest at the negative plate? Oh. Well, the first thing you might think of here is, well, it will be the same, right? It's the same. If you think about the energy of these particles here, they have the same exact potential energy. Same charge, same distance traveled, same electric field, right? Okay, so that means their kinetic energies are the same. And that's true. Their kinetic energies are the same. However, they don't have the same mass, right? An electron and a proton. So while their kinetic energy is the same, there's a difference in the speed because there's a difference in the mass. The electron is going to move a heck of a lot faster here because it has such a low mass. Okay, I believe we don't know the mass of the electron actually. No, we do. Actually, we don't. We know it. It's just so tiny. We don't know the neutrino mass, though. That's the thing. It's small. It has mass, but we don't know what it is. And there's 3 of them. It's pretty wild. All right. So, energy transformation. Potential converted to kinetic. They have the same potential energy. So they lose the same potential energy. They gain the exact same kinetic energy. So really, this is a problem where you just equate the kinetic energy of the 2 things, because they are equal, and you simply solve for the velocity of the electron here. Now it's going to vary as the square root of the ratio of masses, and so the electron's going like almost 1% the speed of light here. So electrons pretty fast. But yeah, that's the idea here, is that potential energies are identical. QES. That's not different for the electron and the proton. But they do have different masses, so they have to have different speeds since they have the same kinetic energy. All right, excellent. Excellent. Now, so dealing with uniform fields is fine and all, but it's not always going to be the case that you deal with a uniform electric field. What if you have an electric field that varies with distance? Okay, fine. This is our formal definition of work, the path integral of force dotted with a small segment of line. And we'd have to evaluate this integral if we have anything that is variable. The reason why we didn't worry about that before is because the value for f was QE, which was constant, comes out of the integral. So let's do it. Here we have a fixed charge. Well, we initially have a fixed charge. It's going to stay fixed. Sorry, this is a fixed charge Q1. We place a charge Q2 at a distance x sub I from the position of Q1. So as a result of being in proximity, right, they're going to experience forces between them, which means they are going to have an equivalent potential energy. At some later time, because Q2 is allowed to move, it's going to travel along the x-axis. The force is going to continue to decrease as it moves away. And so we have to work out the path integral for the work here. Fortunately, it's not too bad because the dot product is gone, because the displacement and the force are always parallel, so that makes that easy. Our ds is actually a dx because we're moving along the x-axis here. And the force, we're going to have to put in our Coulomb's law, right? And so we're integrating 1 over x squared. Okay, if you do that, put the -1 up top. You add 1 to the exponent here, which is actually a -2, so it becomes a positive -1. And we evaluate the limits and we get this expression here, and then we make the same statement. Okay, well, for conservative forces, the change potential energy is equal to minus work. And this is the expression for work, and it has a differential in it. So by the same logic as we had before, each one of these terms represents the potential energy of these charges. And the potential energy is K, Q, Q over X. Looks a lot like Coulomb's law, except it's not an X squared, just an X. Which is a little unfortunate because we have Coulomb's law, right, which is K, Q, Q over X squared. We have the electric field, which is K and only 1Q over X squared. Now we have energy, which is KQQ over just an X. And then next week, we're going to have electric potential, which is K1Q over X. So you're going to have four concepts that are very similar to each other and mathematically similar to each other. And so do you think students mix those up all the time? You would be right. They do. And my advice to you is to not mix them up. All right. Okay, so generally speaking, though, I mean, this was applied just to X, but this is really along any direction because your displacement and your force for 2-point charges are always going to be parallel to each other, so we don't have to use X, we can just use R, a distance away. And so that's what our electric field is. Now, this is strange in a way, right? Because normally, like we did gravity, and when we just did the uniform field stuff, we select a 0 point, right? The ground is 0 point, or negative plate's 0 point, whatever. Well, this thing is never actually 0, right? I mean, not technically. But as R gets really, 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 really large, this approaches 0. And that actually creates an inherent 0 point that we don't change. So this is a situation where the 0 point is set and you don't want to change it because it just matches up mathematically with this term here. So the 0 point is at infinity. Okay? So if you put two charges next to each other, they're going to have a particular potential energy to them. Now, as this one flies away, the potential energy is going to decrease, the kinetic energy is going to go up until it reaches infinity, and then that's when the particle travels at its fastest. But, and while it's asymptotic with 0, it does get to 0 rather quick. I mean, it's a what's the word for that? There's a word for that. When there's different rates at which things are asymptotic. Sometimes they're fast, like sequences can converge quickly or slowly. It's kind of a weird concept, but this thing approaches 0 very rapidly. I'll just put it that way. There's a name for that, though. There's a name when like a sequence converges faster. Right, I don't remember the name for that. Shoot. I don't know. I'll think of it later. Or not. All right, so here's how it's going to look for the positive charges. Now, in this example, the positive charges have been shot at each other. They don't obviously have to be shot at each other. We're just using that as a nice illustration here. But let's say we do have this situation where they're shot at each other. They'll approach each other, and they'll reach a minimum distance. And that minimum distance happens when there is no kinetic energy, and all of the energy is put into potential energy. And in that situation where the kinetic energy is 0, the potential energy will be at its max, and you can solve for a minimum distance. So the graph, a 1 over r graph, is this line that you see here. And there is a certain set amount of mechanical energy in the system, right? When you initially place the charges next to each other, okay, whether you shoot them at each other or not, there is a maximum potential energy, which is our maximum E mechanical. Now that doesn't change, right? Conservation of energy doesn't change. So what happens is as the particles start to fly apart from each other, the potential energy starts to decrease and the kinetic energy starts to go up. And the interpretation on this graph is the following here. I'm going to use, I'm going to use red. So at this distance here, the kinetic energy is this distance from E mechanical, the kinetic energy is the distance from E mechanical down to the line. So you can see how that distance is gradually increasing. because the kinetic energy is gradually increasing. So the interpretation here is the potential energy is the distance from the y-axis or the r-axis up to the line, and the rest of the distance is your kinetic energy. So as the potential energy drops, kinetic energy grows. Easy enough, right? Easy enough. So these things are now. I mean, in reality. Well, I'm not going to talk to you about nuclear physics. I don't know what I was thinking. I was about to tell you about fusion, but that is so off topic. Let's move on. Now the negatives. Having a negative. Well, by the way, this wouldn't. Wait, what? What did I do? By the way, if this is for like charges, I show positives here, right? It wouldn't be any different if you had negatives. It would be the same. Now, what if you have opposite charges? Well, it gets a little tricky, to be honest. If you have a charge that's negative, that means a potential energy term is negative. Negative, right? So what that means is you have the opposite situation where you have a sort of maximum distance that they can be because they're attracted to each other. So imagine they're just they don't have to be shot apart from each other. They can just be, you can just have them at fixed distances and let them go. But what happens is, same deal here. If they're attracted to each other, you can shoot them away from each other and they'll reach a maximum distance, which determines the mechanical energy because at that point, everything is potential energy. And then as they start to fly toward each other, the potential energy continues to decrease, but it does so as a larger negative value. So the potential energy is still decreasing. The potential energy is still zero or infinity. But it gets a little strange here because what happens is you guys start to go here. This starts to approach a distance of zero, right? It won't actually reach zero, but again, more atomic physics there. Now, how do you interpret the kinetic energy here? Well, what happens is this. From the line down is going to represent your kinetic energy. And you can see how that increases as the potential energy continues to decrease. Right? And that's the interpretation here. So it's still the distance between the mechanical energy line and the potential energy line. It just looks strange because it's negative, so it's flipped. Your potential energy is still going down, your kinetic energy is still going up, but the potential energy is negative, so it gets increasingly more negative, which is still a decrease. Right? So that's a little strange. Let's do a problem. I keep saving screenshots. I don't even know where they're saved to. This is the worst day of this week. Worst day of this week. All right, here we go. We're going to do a positive negative example. We have our charges. 6 microcoulomb, 4 microcoulomb. Now it's micro, 10 to the minus 6. Got to be mindful of that. I can't tell you how many times I put the micros in there and people are like, nope, it's nano. Doing nano. It changes, right? All right. They have identical mass. That's nice. 5 grams. Tiny. They're initially 12 centimeters apart. That's their max. Oh, and they are shot in opposite. No, it's not the max then. They're shot in opposite directions with a speed of 10 meters per second. What is the distance of maximum separation? All right, energy transformation. Kinetic to potential, right? As they're shot apart, they're going to slow down. As they get further apart, their potential energy is going to increase. And then when they get to their maximum separation, what happens? You're at this location right here. Right? Oh my gosh. Right there. Where the mechanical energy is all potential energy. And so the kinetic energy goes to 0. So our energy conservation is going to look like this. We're going to have a initial potential energy and an initial kinetic energy. I don't show that here, but there's a little I there. And then over here, it's your U final. Well, there is I can write a K final here, but here's the thing with the K final is that it is 0 at maximum separation. So what we're doing here is we're basically just trying to figure out, what their max separation is. Now, there's one little issue here, right? One little issue. It's possible. Okay, I'm just warning you. It's possible that these things are shot too quickly. What do I mean by that? Well, if they're shot too quickly, they could fly apart from each other and they can just keep going. They can have achieved escape velocity, basically. So I'm going to break this down a little bit more than I normally would. At this point, I'm just like, okay, I'm just going to solve for it. So what I want to do is I actually want to compare my potential energy to my kinetic energy. Okay? I have a negative 1.8 joules when I put in my values for the initial. So initially they're 12 centimeters apart. So the 12 centimeters goes right for R. And then my charges go here, obviously. And I end up with a negative 1.8 joules. Okay. What's the kinetic energy? The kinetic energy, when I put in, I got two particles of the same mass. So I'm just going to double the kinetic energy of one. And I put this initial speed and the masses in there, and I get half a joule. So when you add all those up, we end up with a negative potential energy that's a little bit larger. Okay, negative 1.3 as opposed to negative 1.8. So that's telling us that we are somewhere maybe here on that curve. Okay, the total mechanical energy is negative still. So that's fine. Now, here's the thing. If the speed was really large, right? The speed was really big. Say instead of 10, what if we up this thing to 100? If we up this to 100, well, that's going to make this thing be about 50, right? It's going to be 50 joules. And that's way more than the potential energy. And what that means is they will escape each other, because you'll calculate this up here, and you're going to end up with a positive value here. Well, how can you have a positive value here? Well, it's because your potential energy is 0, and you have residual kinetic energy. So it's a nice little check here. If you end up with a negative, mechanical energy, everything's fine. They're going to reach a maximum distance, and they're going to come back together. But if you end up with a positive one, then they escape. And we wouldn't set this equal to a potential energy, because that would be 0 at infinity. You set it equal to another 1/2 mv squared, and you figure out what the velocity is when it's sufficiently far away. So that's kind of a neat concept here. Anyway, so I end up solving this here. I solve for my R final here, and I end up with a distance of 17 centimeters. So that's what happens. So at 12 centimeters, they're shot apart at 10 meters per second. They reach a distance of 17 where they come to a stop. And then they start to head back to each other. Okay, but I don't care about that part. I just care about the maximum separation here. Excellent. Any questions about this one, though? Anything unclear about it? Move on then. All right. A positive and a negative charge are released from vacuum, from rest in vacuum. They do move toward each other. As they do, what happens? Uh-oh. I don't know. I don't know, people. I'm getting a little concerned now. I don't think I see a single right answer. C. Right? Now, positive, negative charge. That's negative potential energy. So the answer is not A or B. Boom. Simple enough. And what's the graph do, right? They're moving closer together. Let's go back. There you go, right there. As your distance approaches 0, all right? As your distance approaches 0, as you move along this axis here, your potential energy is getting more and more negative. Oh, here we go. What if you have a bunch of charges? They got a bunch of charges. Not just two. You have a bunch of point charges. Well, fortunately, superposition still applies, because, conservative forces, that's a big part of it. But superposition applies, so what you do is you have to add up the potential energy of every pair. So this fancy terminology here, the summation of I and j such that I is less than j, is just a fancy mathematical way of saying you have to compute the potential energy of every single pair of charges. So if you have 2 charges, you have 1 pair, right? If you have 3 charges, you got 3 pairs. If we got 4 charges, what's that, 6? 1, 2, 3, 4, 5, 6, 6. Okay, what's that sequence called? I don't know. Is there a name for that? It's gotta be. My brain is just off right now. My brain's just off. I can't remember anything. What is that called?
Is that the Fibonacci sequence?
Is it? Nah.
I can't remember. I think that's
Really?
could be the wrong one.
Fib? Is it Fibonacci? I got a nice hat. Every time I see images of that guy, I'm like, that's a cool hat. Well, that's a pretty cool hat. It's not Fibonacci. It's not. Gosh, I don't know. I'm thinking about things. Yeah, I definitely recommend Google Fibonacci. Check out this little hat thing there. Apparently he was Italian. Boy, he lived a long time ago. I didn't know he lived in the 12th century. What a maniac. We don't know when he died, though. It's too bad. Oh, whoa. They say he lived to 80. Good for him. All right, anyway. Well, there's a statue of him. Doesn't look anything like him, though. Well, not the picture I know. All right. Here we go. Wrapping it up here. What is the electric potential energy of the group of charges? What's the electric potential energy of the group of charges if the 2 nanocoulomb one was swapped with a negative 2 nanocoulomb one? Now you look at this, and this might be a little triggering for you. You look at this and say, not another one of these. But fear not, we're not doing vectors. Right? This is all scalar stuff. So what we have here, and let's just jump right into this. Let's just go right to it. There we go. The total potential energy of the group of charges is simply taking the sum of every possible pair. So we're going to add up the potential energy from, well, I'm calling the one at the bottom here 1. This is 2. This is 3. So potential energy of the 1-2 pair, the 1-3 pair, and the 2-3 pair. So I have to basically work out all this stuff here. Not too bad. Okay. Now, this is a 3, 4, 5 triangle, right? 3, 4, so the hypotenuse is 5, right? So plug in all your numbers here. Things are in nanometers. No, they're not. Things are in nanocoulombs. Okay? Gotta use meters here, right? You know about that. Don't use centimeters. You have units of joules here. That's got to be SI. And we end up with a 4.8 times 10 to the minus 6 joules. Now, what we're going to do for the example 5 here is we're swapping out number 2, right? So that means you're going to change these 2. So instead of having a positive 2, you're going to put a negative in there. So the potential energy is going to be negative. This first term is negative. Same number, though. The last term is negative. Same number, though. When you add those up, we end up with a different potential energy. Negative 1.5 times 10 to the minus 6. All right, fantastic.